Hi, I'm Carlos Avilés, and this video is a presentation of my diploma thesis with the title GNSS-SDR. It will cover different topics. First, I will briefly present the project and its context. Then, I will introduce the general problem that this work has tried to address, followed by the solution to the problem and how it has been implemented. Finally, we'll go through the conclusions. So let's begin with the introduction. The title of this diploma thesis is GNSS-SDR, which stands for Global Navigation Satellite System Software-Defined Radio. This is also the name of a project that began at CTTC in February 2010 and finished its execution phase in the end of May. I was part of the team that was set up for the project, and my diploma thesis is a product of the work I have done with them. Now, why did this project begin? To understand that, we need to talk about global navigation satellite systems. GNSS is used to locate receivers globally. This technology is well known nowadays. One implementation of GNSS is GPS, which is used to locate cars, people, boats, planes, and anything else carrying a GPS receiver. So GNSS is about knowing your location, but how does it work? How does a receiver know where it is? The idea behind GNSS location is quite simple. If you know the distance between you and some given references, and you also happen to know the exact location of these references, you can calculate your own position by applying trilateration computation. That works just fine, but how do you calculate these distances? GNSS reference locations broadcast accurately synchronized electromagnetic waves which travel from the transmitters to the user receiver at the speed of light. Now, if we send a signal at an instant t, it will reach the receiver at an instant t plus some amount of time. This amount of time times the speed of light gives us the distance between the reference and our receiver. The task of the receiver consists of estimating those propagation delays. Since factors such as electron density content in the ionosphere, multi-path propagation or lack of synchronization within satellites and receivers clock, the obtained measurements are known as pseudo-ranges. From the pseudo-ranges, position, velocity, and time of the GNSS receiver can be computed. The final question is, what are these references and where are they located? GNSS uses satellites for that. GPS, for instance, has 24 satellites orbiting at an altitude of approximately 20,000 kilometers. This set of satellites is able to cover the whole Earth, and their signals are broadcasted constantly and constantly processed by our GPS receivers to calculate positions. As simple as the idea behind GNSS might sound, its implementation is anything but easy. There are many challenges that have to be solved in order to have a GNSS system working in the real world. For instance, research on how to calculate positions with the highest accuracy is constantly being applied. New algorithms are discovered, new approaches are being tested. All this work is done in places similar to CTTC, where highly qualified teams are constantly improving the way GNSS systems are implemented. In this context, the project GNSS-SDR started. Research requires experimentation, and experimentation on GNSS requires a lot of hardware, which is not cheap, and more importantly, it is not flexible. There is no easy way for testing new things without having to build its hardware components or internally reprogramming them. At this point, software-defined radio has to be considered. SDR has a very clear goal: to turn rigid radio hardware into flexible software programs. Flexible in the sense of being easily configurable and customizable. How can SDR improve research on GNSS receivers? Software, as opposed to hardware, can be developed in standard environments that have reduced cost implied. It can be easily reused, shared, and it can run in many different platforms, such as personal computers. Since GNSS involves radio signal processing, a GNSS receiver can be implemented using SDR. As a consequence, GNSS research can be carried out through software modules. This project aims to build a GNSS-SDR receiver using standard software methodologies to ensure its quality. The result will be released under a GPL license. This GNSS-SDR receiver is based on the model presented in the publication Software-Defined GPS and Galileo Receiver, a single-frequency approach. This model can be represented by boxes, meaning specific signal processing tasks, and arrows connecting these boxes that represent the flow of signal samples. So what we have is a flow of data samples originating in the front end. These samples pass through different signal processing stages which apply the required calculations in order to produce the coordinates of the receiver's location. As we see, this model sets a boundary between software and hardware very close to the antenna. The front end is a major piece of hardware that is still needed to perform various tasks such as signal sampling, analog to digital conversion, and filtering. The first processing that is applied to the samples is called data conditioning. This process is responsible for adapting some specific parameters of the incoming signal, such as the sampling frequency or the sample's data type. This is necessary to avoid having an implementation of the signal processing that is dependent on the capabilities of the front end. Right after the data conditioning, we have the specific GNSS signal processing, which consists of the calculation of the distances between the receiver and the satellites. This implies coarse and fine-tuning estimations of the synchronization parameters, processes that are referred to as signal acquisition and tracking. In this model, these distances are called pseudo-ranges and are the input for the processing box at the end of the chain. This module, position, velocity, time, calculates the position of the receiver based on these pseudo-ranges and some additional information that is generated during the GNSS signal processing. The model considers that since we need to calculate distances of different satellites, and for this we must process different signals, it is best to dedicate a set of processing modules to each satellite. This set of modules are called channels, and there is one active channel per satellite signal we are processing. The set of processing modules in every channel is the same. First, the already conditioned samples pass through the acquisition module. At this stage, the incoming signal is used to check the presence of the signal of a specific satellite. If the signal is present, the processing will continue. Otherwise, the channel will be discarded. Once a satellite signal has been detected, it has to be tracked. We need to track basically two values: the carrier frequency and the phase of the PRN code. The frequency of the carrier changes during time because of the Doppler effect caused by satellites and receiver movement. The PRN code, which is used to identify uniquely each satellite signal, varies in phase when the distance between the satellite and the receiver changes. These two values are used to wipe off the carrier and the PRN code from the incoming signal. What is left is the message that the satellite sent. This message includes information that is used to help calculate the distance. This information is extracted in the navigation data extraction module. The last process corresponds to the actual calculation of the distance. Based on that model, we developed a design for a software implementation. This design has its foundations on the channel architecture pattern. This pattern considers sources which put raw data into a chain of transformations that is gathered at the other end by an output. This architecture fits perfectly well with the model we just discussed. Instead of implementing our own channel architecture pattern, we decided to use New Radio for that. New Radio offers a set of C++ and Python libraries to build SDR applications. These libraries offer implementations for managing blocks, which are transformation modules, their connections with other blocks, threads, shared memory, sample data types, etc. New Radio also includes ready-to-use implementations of blocks that are useful in the context of signal processing. After choosing an architecture and selecting New Radio to implement that aspect, we needed to specify more accurately how we were going to define and organize the different abstractions that are present in the model. For that, we focused in three aspects: configuration, flow graph, and control. These three aspects define the most important concerns we considered for that application. The design also focused on three properties we wanted our software to have: simplicity, modularity, and portability.